Hi, my name is Sergey Levine, and today I'm going to talk about reinforcement learning pre-training for reinforcement learning fine-tuning. So many of the most significant advances in machine learning have been accompanied by two basic ingredients, the use of large high-capacity models and the use of large data sets. And that's what has enabled, in addition, of course, to many other technological advances, many of the most exciting things we've seen in ML, from large language models, computer vision systems, translation systems, speech recognition, generative models. They all basically, at some level, rely on this formula. However, if we want to go from machine learning systems that simply predict or detect things in the real world and instead actually make optimal decisions, then we have to think about the kinds of assumptions that underlie our systems that might be a little bit limiting. So typically when we talk about passive prediction or perception problems, we make a number of simplifying assumptions that make it very convenient to use simple and reliable supervised learning methods. For example, we typically assume that the data is IID, meaning that each data point is independent of every other one, that we have ground truth supervision for the label or for the kind of text to produce or for the kind of image to generate, and that the objective is to predict the right label or the right word or the right image. But in many other domains, these assumptions don't really hold. If you want to drive a car, control a robot, perform some sort of operations research problem for inventory management, perform stock trading, prescribe medication or schedule treatment for patients, these are all decision-making problems where each decision can change future inputs so the individual time steps are not independent of one another. The supervision might be more high level, such as a goal, and you typically don't have ground truth supervision. You might not know exactly what is the right action to command to the car in the training data. You have to figure that out based on a high level objective, which is to accomplish the task. And it's probably worth pointing out that it's not just these sort of controls or robotic style problems that look like this. In fact, in many cases, real-world deployment of any machine learning system has similar kind of feedback issues, and the kind of simplifying assumptions that we tend to make in supervised learning don't hold even for the supervised systems. For example, if you are designing an app to suggest routes to people to avoid traffic, well, people would use that app, and that would in turn change the traffic patterns. So in fact, you think you're solving a prediction problem, but you're actually solving a control problem. So once we embrace this perspective that most of the problems we want to solve in machine learning are really decision-making problems, then it becomes very natural to ask, can we use the formalism of learning-based decision-making, which is reinforcement learning, as a kind of universal approach to machine learning problems? And if we want to do that, of course, we have to come back to those two big issues in the beginning, the use of large models and the use of large and high-capacity data sets. Now, the use of large models is pretty straightforward. In general, models and algorithms are orthogonal dimensions, and you can mix and match them however you please. But the dataset question is a really important one. And in some ways, the thesis of this talk is that reinforcement learning consumes data or can consume data in a fundamentally different way from more conventional maximum likelihood or supervised learning systems. So here's a way that we can think about reinforcement learning as a way to use cheap, previously collected data. We have our large model, and we have a large, cheap data set of previously collected data. You can think of this as kind of uncurated data from the internet, and perhaps a limited amount of supervision for the tasks that we actually want to solve. The cheap, readily available data tells us how the world works. It essentially tells us about the world's dynamics. And the limited amount of supervision, this is data with reward signals, tells us what the task is. And I think this is a very natural way to look at a lot of machine learning problems. In fact, the entire field of self-supervised or unsupervised learning takes this perspective, but reinforcement learning, I think, gives us much more powerful tools for doing this. Because with reinforcement learning, you really can use the cheap and readily available data to learn more about what is possible and how the world works, without necessarily assuming that everything in that cheap prior data set should be copied, without assuming that it's desirable. So the kind of recipe you could imagine is that you have a large data set from past interactions that your system has had. So if your system is a robot, maybe it's all the tasks the robot performed, whether successfully or not in the past. And that can be used as a basis, as a kind of data set of cheap prior data that you can use for pre-training. And then when you're given a new task, you can pre-train the best possible model from your prior data and then perform a little bit of additional fine-tuning to really master that task. Now, this is not how people typically think of reinforcement learning, but that's the perspective we're going to take. And in this talk, I'll try to convince you perhaps that this is actually a very good way to look at both the reinforcement learning problem and the problem of consuming large amounts of uncurated or unlabeled data. Now, there's, of course, a little bit of a problem. As I said, this is not how people typically look at reinforcement learning. And in fact, reinforcement learning is actually two different things kind of meshed together. And without disentangling those two things, it'll be difficult for us to come up with a solution to this kind of recipe. Reinforcement learning is first a framework for learning-based decision-making. It tells us how to go from a situation where we're given ground truth labels, y, for inputs x, and we have to just copy the function f of x to go from x to y. Instead, in reinforcement learning, we have a decision-making setup where you have a policy that takes actions A, which do not necessarily have to match the actions in the data set, and that decision then affects the next observation. So that's a decision-making setup. But reinforcement learning is also another thing. Reinforcement learning, as it's formulated traditionally, is a framework for active online learning for control. The classic picture that you'll find if you open up, for example, the Sutton and Bardo textbook is one where there's this cycle where an agent interacts with the world in a loop. The agent chooses actions, the environment responds with rewards and states, and it's a very online picture where you actually learn through active interaction. So you can interact with the world, collect a little bit of data, and repeat this process many times until you converge on a policy. And that's very naturalistic. We like that because it kind of reflects a little bit how we believe maybe humans and animals learn. But it can also be extremely inconvenient because if every time you need to run an experiment, you need to collect data online, that might simply not be practical. What you'd really like to do is just take log data, maybe harvest the data from the web or data from all the past experiments or from all the past episodes where your system has done something before, maybe all the logs you've accumulated, and use that for your pre-training. So almost all real-world learning problems look like decision-making problems, but almost all real-world learning problems make it very difficult to be fully active and online the way that traditional reinforcement learning prescribes. So what we need to make all this work to get this nice offline pre-training, online fine-tuning picture to really emerge is a data-driven way to think about reinforcement learning, where instead of having this kind of online paradigm, we'll keep the decision-making part, but get rid of the requirement to be always active on online. And that means replacing the kind of traditional on-policy RL cycle with an offline reinforcement learning cycle, where we take prior data, distill that data down to the best policy or value function that we can get, and then from there, we could do some additional online fine-tuning. And both of the works that I'll discuss in today's lecture are actually based on this principle. So the recipe that we're going to try to develop is one where you take a large data set of diverse but possibly low quality behavior, like all the past interactions, use that to perform some kind of offline learning to get the best possible initialization. And there are a few choices here, like you could do offline training with a set of human-defined skills, or goal-conditioned RL, or even self-supervised skill discovery, and we'll actually talk about a few of these in today's talk. And once you've done that, you can use that as an initialization for then learning a downstream task very efficiently, leveraging this offline pre-training. And that could be done with online RL. It could also be done with offline RL. Conceivably, it could even be done with supervised learning. So you could actually use reinforcement learning as an initialization for downstream supervised learning skills, which might be a good idea if you have this kind of low quality data that tells you what could be done, but not necessarily what should be done. In this talk, I'll only focus on pre-training for downstream online RL, but the extension to fine-tuning with other methods is actually relatively straightforward. So I'll discuss two main projects today that are very complementary in the sense that they tackle different facets of this recipe. The first deals with the question of how to perform efficient online RL after offline pre-training. So this is really focusing on how do we do the offline pre-training so that downstream online reinforcement learning initialized from the thing that we pre-trained is actually going to work. And then I'm going to talk about an unsupervised offline pre-training procedure that doesn't assume that the prior data has rewards, or that it's even segmented into tasks, or even that the prior data has actions. So the goal is to learn entirely from the kind of passive static data that you might harvest from the web, such as video data. And these are complementary in the sense that the first project really deals with basic algorithms and how to make the online fine-tuning work, and the second deals with the right way to formulate pre-training. So let's start with the more algorithmic topic. First, a quick primer to the basic concepts underlying off-policy and offline RL. In reinforcement learning, we have an agent that interacts with the world, and the agent selects actions, and the world responds with states and rewards. And the goal is to find a policy, pi of a given s, that maximizes the cumulative reward that the agent will receive. So not the reward right now, but the reward summed over all future time steps. And a very useful object for doing this is something called the Q function. The Q function tells you if you start in a particular state, then take a particular action, and then follow the policy pi thereafter, what is the total reward that you will accumulate? If you can get a Q function for a particular policy, then you can recover a new policy that is as good or better as the one that you started with by simply being greedy with respect to the Q function. So take an action with probability 1 if it's the argmax. And that's the basis for something called policy iteration. You could also cut out the middleman and directly implement Q-learning, where you try to enforce that the left-hand side and right-hand side of this Bellman equation should be the same. The intuition of how these are connected is that the max is what you get when you plug the argmax into the Q function. So in a sense, Q-learning is like policy iteration, but just omitting the policy extraction step. So if you can somehow make the left-hand side and right-hand side of this equation equal, then you will get the optimal Q function, and its corresponding greedy policy is guaranteed to be the optimal policy. Now, of course, in practice, we can't do this exactly for all states and actions. So what we do is we generate some samples and we minimize the squared difference between the left-hand side and the right-hand side on those samples. And that's where actually a lot of the trouble starts. So I'll give a little bit of a recap of basic offline RL concepts, but essentially the main difference between offline RL, where we learn from a static data set, and online methods like Q-learning is that offline RL has to deal with the distributional shift, the discrepancy between the distribution of states and actions seen in the training data and the distribution over states and actions that will be seen when the learned policy is actually executed in the real world. Okay, so where do we suffer from this distributional shift? Well, this is that Bellman equation again, and I'll rewrite it in a different way to just make the problem a little bit more apparent. I'll replace that max with an expected value under a distribution pi nu, where pi nu is the argmax policy. So I didn't actually change anything because the Q value of the argmax is exactly the max. I just written in a way that makes it obvious that in order for this to work, you really need the expected values under this distribution pi nu to be accurate. And if you ever want to know whether a learned function is accurate in expectation under some distribution, then the first question to ask is, how is that function trained? Right, so let's say that these are our target values, y. The training objective is to regress Q onto y in expectation under the distribution of states and actions in the data set. And we'll call that distribution pi beta, where beta stands for behavior policy. So whatever unknown policy generated our data set, our training objective is a sample-wise approximation to the expected value under that distribution. And of course, we know that if we minimize some loss in expectation under a particular distribution, assuming we don't overfit, then we will expect to have low error under that distribution, but not necessarily low error in expectation under other distributions. So we expect good accuracy when pi beta is equal to pi nu, but of course that's not going to be the case, because the whole point is to find a pi nu that improves over pi beta, and even worse, we select pi nu explicitly to maximize the expected value of the Q function. And that's very bad news. Those of you that are familiar with things like adversarial examples will immediately recognize that this is a recipe for disaster, because if you optimize with respect to the inputs to a neural network to optimize some function of its outputs, then you will very often find a way to cheat. You'll find a way to produce some adversarial input that fools the network into producing the output you want. So in the same way that you can add adversarial noise to fool an image classifier, you can pick essentially adversarial actions to fool a Q function. And that's what happens if we use this kind of method naively. If we use naive Q-learning with offline static data, this is a standard benchmark, the half-cheetah benchmark. For different data set sizes, we get rewards of about minus 250. But if we actually inspect the Q values and see what the Q function thinks it's going to get, the y-axis here is a log scale, it thinks it's going to get somewhere between 10 to the 7th power and 10 to the 20th power. So it's massively overestimating the return it's going to get, which is exactly what you would expect from this kind of adversarial examples perspective. So there are a variety of ways to mitigate this that we've developed in our prior work. The one that we're going to build on in this project is called conservative Q-learning. And the idea in conservative Q-learning is actually quite similar to adversarial training. So we have this overestimation problem. What we're going to do is we're going to find those places where our learned function overestimates and try to push them down. So here's the objective for conservative Q-learning. The second line is just the standard Bellman error minimization. This is just that Q-learning procedure. Minimize the difference between the left-hand side and right-hand side of the Bellman equation. And the first line you can think of as a kind of adversarial term. We're going to find this distribution mu that maximizes the Q values, and then we'll minimize the Q values under mu. So we'll find the largest Q value actions and we'll push them down. It's a lot like adversarial training. Now, in reality, we actually modify the algorithm a little bit to make it more practical, but that's basically the essential idea, that we're going to minimize the high Q values. And this has some very appealing theoretical properties, such as, for example, provably avoiding overestimation. But while this provides a very effective offline RL procedure, it has a little bit of a problem when it comes to offline pre-training followed by online fine-tuning. And that's what we're going to deal with in this talk. So let's talk about offline fine-tuning. Let's say that we use conservative Q-learning to pre-train on offline data, and then we use that conservative Q function, which now does not overestimate, to do some additional online training. If we try to do this naively, we get a little bit of a problem. So this plot shows the online phase after offline fine-tuning with two different methods, IQL and CQL. So CQL is the conservative method I described before. IQL is implicit Q-learning, which is based on slightly different principles, and it's added here more as a baseline. Now, both methods started at a score of about 0.47 roughly from offline training. You can see they both start there. And CQL immediately drops and then comes back up. And IQL doesn't drop, but it goes up very slowly. And that's kind of what we would expect from IQL. I won't talk about IQL too much here. It suffers from a slightly different problem. I'll focus instead on CQL because that's what we're going to aim to improve in this project. So the problem is that there's this drop right as we start fine-tuning. And the entire first period of training, that 30,000 steps, is essentially spent recovering from that drop. That's bad for a few reasons. Like, first of all, it's bad because training is slow. Like, it could probably be much faster. It could be that you'll reach maximum performance within that 30,000 steps, and instead you waste that whole time recovering performance. It's also really bad from a safety perspective, because if this were a safety critical system, the drop in performance would likely correspond to many, many unsafe events. So if you're hoping to use offline pre-training to recover a safe initialization, this whole drop business really completely negates that. So that's a really big problem. If we inspect the values of the Q function a little bit more, we can see an interesting pattern. So these two plots, they actually show both the offline and the online phase. So the first 50,000 steps are offline, and the following are all online. And that little red highlighted part starts exactly when we switch from offline to online. And now there's a pattern that should be very apparent. So you can see here that right as we switch from offline to online, the numerical value of the Q values, basically how well the Q function thinks it's going to do, skyrockets. And at the same time, the success rate drops. Okay, so that can't be a coincidence. Like, somehow, as soon as we start collecting online data, we start thinking that we're going to do a lot better, and we start doing a lot worse. Why is that? Well, the issue actually at this point is not that we're overestimating anymore. The issue is that we're underestimating too much. So conservative Q-learning is quite effective at avoiding overestimation, but the cost that it pays is that it results in Q values that are uncalibrated, in the sense that they do not reflect the true Q values very accurately. The relative Q values of different actions might be reasonable, in the sense that a better action will have a higher Q value than a worse one, but their absolute numerical value doesn't reflect the actual return the policy will get when you run it. And that kind of makes sense, right? Because if your aim is to be pessimistic for unseen actions, well, in large continuous action spaces, every action is unseen to some degree, so it's only a matter of how pessimistic you're going to be. So conservative Q-learning will always create a little bit of an underestimation bias. And it's underestimating too much during the offline phase, and then when it starts getting that online data, when the online data hits the buffer, now immediately it starts seeing much higher returns than what it saw before. That creates very large gradients, which essentially scramble that initialization. So then it wastes a lot of effort recalibrating the value function. That's what that drop and recovery is actually doing. And during that process, the relative ordering of the actions is scrambled a little bit, and that's what accounts for the drop in performance. So essentially, because the offline pre-training is so uncalibrated, the process of recalibrating the value function to bring the values back up to their true levels is basically pretty traumatic. And in that process, the actual values don't mean much until they recover the correct quantitative magnitude. Okay, so it turns out that there's a very simple solution to this. The solution is essentially a one-line change to the algorithm, but the interesting part about the solution is actually some of the theory and the really good empirical performance that this enables. So the key idea is that we need to put the offline trained value function on the right scale. And we refer to this as calibration. So we say that a Q function is calibrated intuitively if it's on the right scale, if the numerical values roughly match the actual returns. Now, the formal definition we're going to use for calibration in our analysis is actually perhaps a little counterintuitive, but hopefully I can convince you that it makes sense. So formally, we're going to say that an estimated Q function for a given policy is calibrated with respect to a reference policy, mu, so mu is some other policy, maybe not a very good one, but it's some kind of real reference policy, if the learned Q function is always greater than or equal to Q mu. Okay, this is a little strange because saying calibration means that you're always larger, but assume mu is not a very good policy. Like it's kind of somewhere mediocre, something average. So it's pretty reasonable to say that pi, the policy that you learn, is going to be better than mu. Not because pi is awesome, but because mu is not so good. So all this is saying is that you should learn Q values that are an upper bound on the true Q values of some not so great policy. So this is not a very high bar. This essentially means, for example, that if your rewards are always 0 and 1, which means the Q values should also be between 0 and 1, well, you shouldn't get Q values that are less than 0. It's very basic stuff like that. So calibration basically means that the learned values upper bound the values of some real policy. It's really not a very high bar, but CQL will often violate this because CQL will push down those values quite far. Conservatism, which is what CQL enforces, says that the learned value should lower bound the value of the learned policy. So you're learning a policy pi, the values you get should lower bound it. Now, of course, if the reference policy is the learned policy, then calibration and conservatism together imply that your Q function is perfect. That's a very high bar. So mu cannot be equal to pi. If mu is equal to pi and you want both calibration and conservatism, then you essentially want perfection. That's impossible. But if mu is significantly worse than pi, then having both calibration and conservatism is not a very high bar. And surprisingly, it's easy enough in theory to show that as long as you're calibrated with respect to any reasonable policy, you're going to get efficient online fine-tuning. That's not at all obvious. It's actually quite surprising. But this is basically emphasizing that this calibration requirement is not actually a very stringent requirement. It's just saying you should not be lower than the value of some policy. Now, of course, the bound that we're going to get on regret is going to depend on the value of that policy. So the better mu is, the faster you'll fine-tune online, and that makes sense because if mu is as good as pi, then of course you're basically done. Like you have a perfect Q function. But you can actually get a decent bound even with a fairly bad mu. Okay, so how can we ensure that our Q function is calibrated? Well, before we were doing this mean squared error regression onto the target values, minimizing the difference between the left-hand side and the right-hand side of the Bellman error for the states and actions that we sample from our behavior policy. Now we're simply going to replace that with regression onto the larger of the two values, the larger of the target value y and Q mu. So essentially for every training sample, if the target value is lower than Q mu, then we'll replace it with Q mu. So that means that our targets will always be greater than or equal to Q mu. Very, very simple change. Of course, the trick is we need to actually get Q mu somewhere. So if we had Q mu, if we knew the true Q values of the reference policy, this would be quite easy to do. Okay, so how do we get this? Well, the trick is that we have the liberty to pick a mu. And the mu that we're going to pick is the behavior policy. That's very convenient because our data is sampled from the behavior policy. So the behavior policy is one of the few policies for which actually estimating the value is not too hard because we have entire trajectories sampled from pi beta. And in that case, we can get an unbiased estimator for the Q values of pi beta simply by regressing onto the sum of rewards that we actually observe in our data. So for that, we don't need any temporal difference learning. We just literally sum up the rewards that we've seen in the training trajectories and use those to get Q mu. If mu is pi beta, then Q pi beta is just approximated with a sum of discounted rewards that we've actually seen. And pi beta is the only policy for which we can do this with offline data because that's the only policy that our data actually came from. So we have this because our data actually consists of trajectories from pi beta. And there's no distributional shift here because we're training in expectation under pi beta. So we're going to use pi beta to estimate these and we're trained under it. So this is actually the only policy for which we can get these values. So the complete method is actually a very, very simple, very small change to CQL, which we call CalQL for calibrated Q learning. So we have our conservative Q learning objective from before, and the only difference we've made is that we've changed those target values to be the max over the estimated target value from our current Q function and Q pi beta estimated via Monte Carlo regression. So it really is just a one-line change. And this is what ensures that calibration. And then the regularizer, just like before, ensures conservatism. That ensures the lower bound property. So the max ensures the upper bound, that we're always greater than or equal to Q pi beta, and the first line ensures the lower bound, that we're always less than Q pi. And it turns out that if we have this property, we can prove a theorem that shows that the regret that we get if we initialize from this Q function and then run online RL will actually, in fact, be bounded. Now, the bound is a little bit complex. I won't go into the details of this bound, but it's a pretty good bound. You can read the paper to find out more about it. But the intuition is basically that online RL fine-tuning is provably efficient, meaning that you get low regret, if the pre-trained Q function is both conservative and calibrated. And the better the policy against which it's calibrated, the more efficient the online fine-tuning is. So you can see that here. So V mu is how good the reference policy is. So of course, the better V mu is, the lower the second term in the min is, which means you can get better regret. But even if the behavior policy is not so good, the first term could dominate, and that will still bound your regret. So this is actually quite a nice result that shows that, yes, we do actually get efficient online fine-tuning if we ensure both conservatism and calibration, and the stronger the policy against which you calibrate, the better it will be, which is kind of an obvious conclusion. Empirically, CalQL does very well, so we tested it on a variety of tasks, the D4RL benchmark tasks, as well as a vision-based robotic manipulation task in simulation. That's the one shown on the right side. These are the plots. So the first 4 plots are for the ant maze. These are difficult navigation problems in D4RL. The second one is kitchen manipulation tasks in the Franca kitchen. That's on the left side, as well as the visual manipulation on the right side. And the lower set of plots is the sparse, adroit, dexterous manipulation tasks, which require controlling a 5-finger robotic hand. That's the second plot, the second figure on the top, which is also a very high-dimensional and very complex task. In all of these plots, the red curve is CalQL, and this is always showing only the online fine-tuning phase. So the offline phase is off-screen in all these cases. And you can see that CalQL, in some cases, is just significantly better than all prior methods, like in the kitchen tasks, or on the largest and most difficult ant maze tasks. In other cases, it sometimes ties with prior methods. Sometimes it is tied with CQL. Sometimes it's tied with IQL. But the interesting thing is that CalQL is the only one that is consistently tied for the best place. So the actual best prior method, you can see it varies a lot. For example, in the bottom row, relocate binary, the bottom right plot, they're simply running naive soft actor critic with offline data is the most competitive baseline, and both IQL and CQL do a lot worse. Whereas, for example, kitchen partial, the first plot in the second row, there CQL is the most competitive method. For pen binary, the bottom left, IQL is the most competitive method. But in all of these cases, CalQL is comparable or better to whatever the previous best method is. So that's a really good sign. We've also experimented with maximizing the efficiency of online fine-tuning with CalQL, where we can actually increase the number of gradient updates. And here we compare to RLPD, which is a very recent paper also from our group, that shows a few tricks, not for offline pre-training, but actually just for online training with the buffer initialized from offline data, where we can enable very high numbers of gradient steps. So the UTD number updates per time, that's the number, that's the frequency of gradient updates. So the larger that value is, the more updates you're making. Doing more updates leads to overfitting, so it's actually quite difficult to design a method that can accommodate extremely high UTD rates. And you can see that in these cases, CalQL with 20 updates matches or exceeds the performance of our LPD, and it also starts out higher because it actually benefits from that pre-training. So empirically, the results are quite good. The key takeaways from this are that online fine-tuning from offline RL initialization is non-trivial. There are very real problems with it, but we can make it provably efficient with a very simple one-line change to CQL, and this performs very well empirically. So that can get rid of that dip, that period of highly unsafe behavior that we found often accompanies offline initialization. So this is very promising because, of course, if you want safe online fine-tuning from offline initialization, you really need to get rid of that dip, because otherwise this is going to be really bad news. Okay, so that was kind of the algorithmic core of the talk. The next part I'm going to talk about has more to do with representational learning and leveraging more diverse sources of data. So remember how I mentioned that the recipe is to use a big data set from past interactions, and there are a few ways to use it, such as human-defined skills, goal-conditioned RL, or self-supervised skill discovery. Now, in the previous project, we didn't really worry about this. We just said, well, the offline pre-training is going to be exactly on the same task as the subsequent online fine-tuning. But of course, in general, that's not going to be the case. You're going to have very diverse sources of prior data. They might not even all be data from your particular system. So maybe you're controlling a robot, but your prior data might consist, for example, of videos or something else. Well, in that case, you need an algorithm that can accommodate that. And in that case, you can't even assume that you have the same action space or the same set of interventions available to you, so that exposes a few interesting algorithmic challenges. But I should say that the methodology I'm going to describe is not actually specific to learning from data without actions. It can just as well be applied to learning from diverse data without rewards, data that hasn't been annotated in any way at all. And in general, I think it offers a very powerful engine for leveraging kind of internet scale data in the future to enable offline RL pre-training. Okay, so here's the basic principle. We're going to have some prior passive data, and we use the term passive data to broadly denote data sources that could be from with other action spaces, other embodiments, or even video data without any actions at all. So we assume that this passive data has no rewards and no actions. It simply consists of sequences of states. We do assume that it's sequential. We're going to use this prior passive data to learn what we call an intention condition value function. So in this intention condition value function, I'll explain the symbols in a second. The important thing is that in place of actions, we have a notion of latent intentions, which we're going to denote with Z. Roughly speaking, latent intentions correspond to the algorithm's inference about what the agent in that passive data is attempting to accomplish. Now, crucially, the data doesn't have to be optimal for that. And in fact, the algorithm we're going to develop will learn intention condition value functions that are more optimal than the average behavior in the data, just like offline RL learns behaviors that are generally more optimal than what is seen in the data. And then we're going to extract representations from this intention condition value function that will make downstream RL much more efficient. So our goal will not be to actually just zero-shot solve a downstream task. Our goal will be to use this intention condition value function for representation learning, just like we discussed in the motivation in the beginning. Okay, so what is an intention and what is it that we're going to learn? What we're going to learn is an object that answers this type of question. Let's say that you're a robot in a kitchen, starting from this state. Will I open the cabinet if I act to fetch a plate? So the pink part, open the cabinet, is the outcome. The fetch a plate is the intention. And the blue part, the state, that's the state. So Z is the intention. This S plus is the outcome, and S is the state. So this V S plus Z literally means if I'm in state Z, how likely am I to reach S plus if I'm attempting to do Z? And if you want kind of a semantic meaning, then Z roughly might mean something like fetch a plate, and S plus might mean open the cabinet. So it's an object with three arguments: the current state, the outcome that you're trying to evaluate, and the intention that you have. And notice that the intention and the outcome are not the same thing. Of course, your intention is to achieve the outcome that matches the intention. Like if you're trying to open the cabinet, if you're trying to fetch a plate, the outcome you'd really want is I fetch the plate. But we're going to try to learn the likelihood of other outcomes. And there's actually a very good reason for it, because of course we're not assuming that our data is optimal. So it may be much easier to learn very expressive intention condition value functions that evaluate likelihoods of other outcomes rather than the one that was intended, because it may be that the data supports that a lot more effectively. Okay, so this is a little bit abstract, but I'll make it much more concrete in a second. Each intention essentially defines a transition. So an intention determines a policy, and the policy in turn determines a transition. We can write this in a very Bayesian way by saying that the probability of S prime given S comma Z can be obtained by summing over all actions, or the probability of that action given that intention times the probability of the transition. But remember that we don't have actions in our data, so we can't actually evaluate these quantities. We can't like learn P of A given S comma Z. So in a sense, what we're learning is is the probability of future states given the current state intention, which kind of integrates out the action and effect. So this maybe gives you a little bit of intuition for how we can do this without actions at all. Okay, but to start putting together the mathematical description of this, let's first do a little bit of linear algebra. Let's take these probabilities, and these are probabilities of one-step transitions, and put them into a matrix. So let's define the matrix PZ so that the entry SS prime in the matrix PZ is the probability of S prime given S comma Z. So this is a matrix where the number of rows and columns is equal to the number of states. Disregard for a moment the fact that if our observations are images, this thing is going to be enormous. Let's pretend that we have a small discrete state space. Maybe we have only 32 states total. Then this is a 32 by 32 matrix for every intention. Every intention has a different matrix. And if you have a transition matrix like this, which defines a Markov chain, you can train what's called a successor representation. This goes back to the work of Peter Dayan in 1993. The successor representation is given by this formula, and intuitively what the successor representation tells you is, if I have a probability of termination of 1 minus gamma at every step, how likely am I to terminate in a particular state if I start from another state? So if the transition matrix is the probability of the state at the next time step, the successor representation is the probability of that state under a geometrically discounted future. So if I'm executing intention Z, how likely am I to eventually end up in a particular state S prime? And the successor representation obeys a version of the Bellman equation. So the successor representation for SS plus is equal to a delta function that S is equal to S plus now, plus gamma times the probability that will be equal in the future. So if you want an intuition for what this M means, basically every entry SS plus in MZ is the probability that you will eventually land an S plus if you're starting an S. So this is the probability of S plus at some geometrically distributed future step. So that kind of maybe might already intuitively suggest to you what that has to do with this example. Will I open the cabinet in fact to fetch a plate? Well, if fetch a plate is the Z, open the cabinet as the S plus, then MZ SS plus will give you that probability. So if we use E with a subscript to denote a canonical vector, so E subscript S is an entry with a 0 everywhere except for a 1 in the position corresponding to S, then this intention condition value function can be written as ES transpose MZ ES plus, essentially indexing into the matrix MC to pull out the entry in the row S and the column S plus, which is basically the probability that you'll eventually land in S plus if you're currently in S and you follow the intention Z. Now that's not actually how we're going to do it, because of course in reality we have a huge number of states. Each of these vectors would have a dimensionality equal to the number of states. The matrix would be S by S, which is enormous. So this only works in small discrete state spaces. We'll have to generalize this in some way to get it to work in large, continuous, or infinite state spaces. But for now, let's stick with this intuition, and let's see what we can do with these kinds of representations. So remember that MZ SS plus is the probability of eventually getting to S plus at some geometrically distributed future step. So that's our intention condition value function. The probability that a future state is S plus, given that we're in S, and we're going to follow Z. Okay, if we have such a thing, can we somehow get the value function for a particular reward, right? This is a reward agnostic object. It only really deals with dynamics and policies. But let's say that we're given a reward function. Well, the value function for a particular reward, let's call it VR, can be expressed as a sum over all possible states of the probability you'll land in that state, given S, and given that you follow the optimal policy, times the reward at that state. So this is basically the expected reward. The value function is the expected reward. But of course, the probability here has to be conditioned on the optimal policy for R. So VR of S is the probability, is the expected reward if you follow the optimal policy for R. So you can actually write it in kind of an analogous way. So if M denotes a successor representation, if you compute the successor representation for pi R star for the optimal policy for the reward R, then the expected reward can be expressed by just summing over all the states of M SS plus pi R star times R of S plus, which can be written in matrix notation as the canonical vector ES, which left multiplies M pi R star times the vector R, where the vector R is just a vector where the reward at every state is in its corresponding entry. So R is a vector with S entries. The first entry is the reward at state 1, the second entry is the reward at state 2, and so on. So that's what that last symbol represents. So now we've written it in a way that kind of looks a lot like the intention condition value function up above, with the difference that the intention condition value function has MZ and we have M pi R star. So how to make sure that we have a Z such that there exists some Z where MZ is equal to M pi R star for each R. If we can do that, then we've basically just learned how to solve every possible RL problem. That's pretty exciting. Well, the key idea is that Z is a vector, so let's just make it the reward vector. Let's literally set Z to be R. If we set Z to be R, then the value function for any reward can be expressed as the canonical vector for S times MZ times Z, or VSZZ, where Z is just R. Okay, this is a little bit kind of simplistic because you're saying, well, okay, you just made Z be R, like it's a little circular, but it works. Like mathematically, it's a perfectly legitimate thing. And what this basically says is that if you learn the intention condition value function for all S, S plus, and Z, then you can recover the value for any reward just by plugging in R for Z in both the second and third argument. Okay. Now, so far we still haven't addressed this issue where all of these things are completely intractable in large state spaces. So let's do that next. So the problem, of course, is that all these vectors and matrices have a dimensionality equal to the cardinality of the state space, which is in general going to be infinite. So what we'll do instead is we'll do all this in feature space. So instead of having a canonical vector for S, we'll have some feature representation of S. And we'll have some feature representation of S plus, and instead of calling this matrix MZ, we'll call it TZ just to denote that it's also in a feature space. So the first vector is a feature representation of the present, the last vector is a feature representation of the outcome, and the thing in the middle is a matrix representation of the intention. And what about rewards? Well, before we would set the reward to be R, but of course that's impractical because R, lives in a space with dimensionality equal to the state cardinality, and now we're going to a feature representation. So here's an interesting way to derive what we should do with rewards. The vector R can also be written as a sum over all possible states of the canonical vector for that state times the reward of that state. So if that's how we're going to do it, then we can simply, just like we did on the left, we can replace the canonical vector with its feature representation. So if we replace ES plus with psi of S plus, now everything lives in this feature space as well, and now we have Z's in the feature space that we can recover from any reward function. And I should mention that this last trick about doing this projection of rewards was actually not invented by us. It was actually borrowed from a very nice paper that introduces something called the FB representation by Toadi and Olivier, called Learning One Representation to Optimize All Rewards. The difference here is that we're doing this without actions, and we have this explicit multilinear decomposition into phi, psi, and t. Okay, so that was kind of a lot to take in, but the short version is that the intention condition value function is a kind of feature space generalization of successive representations. If we can learn it, then we can recover the Z for a particular reward just by averaging together the feature representations of all the states weighted by their reward. And we can devise a way to train this, and that's what we're going to talk about next. So how do we train this whole thing? Well, just like successive representations, these things can be trained with a procedure that resembles temporal difference backups. So in the same way that the optimal Q function obeys the Bellman equation, this thing also obeys a kind of Bellman equation that says that the V SS plus Z should be equal to the delta function for S equal to S plus. So that's just saying, like, if you reached S plus right now, then of course it should be a 1, plus gamma times the probability that you'll reach it in the future. But there's something very delicate about this, because the probability you'll reach it in the future is in expectation under P of S plus given S comma Z. And this is very delicate. So the first term is the probability that you reach the outcome now, which is 1 if it's equal. And the second is the probability you'll reach it in the future if you follow the intention Z. But there's a really big problem. The problem is that you only have transitions SS prime in the data. Those transitions might not be optimal for any arbitrary Z. So you don't actually have samples from P of S prime given SZ. You just have samples from P of S prime given S and some unknown intention. So the solution intuitively is going to be to take our data, our SS prime data, and to weight the transitions by how optimal they are for a Z that we sampled randomly. So we're going to sample a transition from the data, we're going to sample a Z randomly, but then instead of training on that naively, we'll weight it by how likely is it that that transition goes with that Z. There are a few ways to determine this. The particular way of doing this that we're going to use makes use of the advantage. So if we have an S prime, an SS prime, and a Z, we can basically say, what's the reward plus the next value minus the current value for that Z? So that's basically saying for this S prime that I have, how much better is it for this Z than any other S prime? So you'd expect that the S prime with the largest advantage is the one that is the best for that Z. So is S prime a good next state if our intention is Z? And remember that VR is VSZZ, so that's why you see SZZ showing up there. That's basically the value function for a reward R, and that's the reward that corresponds to Z. So if this advantage is high, then this is a good transition for Z. If it's low, then it's a bad transition for Z. So we're going to use this advantage to determine a weight, and that will allow us to train on offline data. So here's the training procedure. Sample SS prime from this passive data set of internet data. Sample Z randomly, and there are many possible choices for which distribution to use. It's somewhat delicate to get this right. The prior paper, the FB paper by Toadi and Olivier, discusses this a little bit. We make a slightly different choice, but I don't want to hammer on this too much because I think that there's actually many choices here that would work. Then compute this advantage, and then sample a future state. And there are a variety of ways to sample a future state S plus. You can just sample it randomly from the training trajectory, which corresponds to a kind of hindsight relabeling. But again, there are many ways to do this. And then compute a weight. And there are, again, a variety of weighting schemes that could be used, some based on importance sampling. The one that we use actually implements an expectile loss similar to implicit Q-learning by Kosterikov et al. This is not the only choice. The intuition is that you just want W to be some monotonically increasing function of A. In this case, this is going to be a function that gives you a large number for positive A's and a small number for negative A's. And then we're going to implement a TD loss, which is weighted by this W. So it's just the difference between the square difference between the left-hand side and right-hand side of that Bellman equation multiplied by W. So if this is a high advantage transition, then we're going to put a lot of emphasis on this. If it's a low advantage transition, we're going to put less emphasis on it. And then we're going to update phi t on psi with gradient descent on this loss. And of course, in reality, we use multiple samples rather than just one to implement mini-batch gradient descent, but that's basically the idea. And then repeat. Okay, so once we train this thing, there are a few things we can do. We can do zero-shot recovery, just like in the FB paper. So we could compute S by doing this reward-weighted average of size, and then just use VSZZ as our value function. Or what we actually do in our experiments is simply use this for feature extraction. So pull out phi of S to represent the value function for downstream online RL. For example, once you get actions, you can represent the Q value of some state in action as phi of S times a W vector for the actions, which kind of corresponds in a discrete action space to just having a different head for every action, just like in regular DQN. So you can use phi of S as your encoder, and then you put a different readout head for every possible action to get the Q values of the individual actions. So that's similar to essentially running DQN with the conv stack initialized from phi of S. So it's a very simple kind of representational learning way of using this object. Okay, so there's a little bit of theory. This is not a very theory-heavy paper, but the theoretical result is essentially that the phi of S that you get is sufficient to represent downstream value functions under some strong assumptions. So the assumption is that you've learned phi, psi, and t so that the approximation to the true intention condition value function over all states and actions, overall state pairs, point-wise, is bounded by epsilon. If you succeed at doing that, then your ability to estimate any downstream value function for any downstream reward will have bounded error. And the error is bounded roughly by epsilon times the sum of all the squared rewards. So this basically says that if you learn a very accurate ICVF, it can accurately represent value functions for downstream rewards, which means that it should be a good feature initialization. Empirically, this tends to work really well. So the first result, which is a little bit of a diagnostic result, we take the ant maze tasks from D4RL. So these are these difficult navigation tasks where you have to control a quadrupedal robot to run around a maze. And we pre-train on the offline dataset, pretending as though it didn't have any actions. So of course, in reality, the dataset has actions, but we simply remove them for pre-training. And we're going to compare ICVF, shown in purple, to a variety of previous representation learning methods. So VIP uses a kind of a temporal distance learning style approach. Curl is just a contrastive representation learning method from prior work. And CPC is a very classic contrastive representation learning method. RLV is a little different. RLV actually tries to pull out a policy from a combination of offline and online data. So that's why RLV starts off a lot higher. Whereas all the other methods, they're just representation learning methods. So the Q function starts off learning from scratch, but with those features. So you can see that that's why all the other methods start off very low. But ICVF gets to by far the highest performance at the end and has the fastest learning, with the exception, of course, that our RLV starts off higher. The plot on the right shows the error in predicting the optimal value, and you can see that there ICVF is much better, which indicates that the learned representations are very good representations for representing value functions. This is an experiment that studies changes in embodiment. So here, the goal is to use a variety of these little funny-looking robots to move all the boxes into the top pink area. And you can either be like a circular robot with arms, or a rectangular robot, or a big rectangular robot. So here we're going to use either data from the same embodiment for pre-training ICVF, or data from other embodiments. And you can see that in the cross-embodiment setting, ICVF does much, much better than all of the prior methods, indicating that it can effectively utilize data from other systems that are structurally similar but distinct. Now, these are kind of simpler experiments. The more complex experiment we have is on Atari games, and the twist here is that the data is actually harvested from the web. So we actually ran a scraping script to scrape videos from YouTube of people playing Atari games. Notice the second figure here is actually a little tilted. I'm pretty sure that's a phone being pointed at somebody's screen, recording them playing Qbert. So these videos, they really are kind of all over the place. And we can use them to pre-train with ICVF and then fine-tune to real Atari games. And here again, we're comparing to a variety of prior representation learning and RL-based methods. And across the board, ICVF does quite a bit better than all of these other techniques. So the takeaways, we can pre-train representations via an RL-like method on passive data without any actions. These representations are provably sufficient for downstream tasks, and we can pull out representations from this that significantly outperform prior representation learning methods. So just to conclude, what I want to leave you with is a summary of this hypothetical pipeline that these kinds of techniques could enable, where we have RL algorithms that use diverse sources of prior data, including passive data and data from past interactions, to learn, perhaps with human-defined skills, or more likely in an unsupervised or self-supervised fashion, to produce representations with offline RL that can then be used to greatly accelerate downstream reinforcement learning. I discussed two works that get at this, the first by making it provably efficient to perform online training, and the second by being able to leverage passive data. I think there's a lot more to be done in this area, but I think that if we're successful, we can eventually get to the point where offline reinforcement learning really is the method of choice for pre-training on diverse sources of prior data. Thank you for listening.